Hi guys, welcome back to my YouTube channel IBwontcrushyou, and today we're dealing with application of functions, and this topic basically shows how we use functions in real life. So let's get started. Problem 1. The cost to park at a shopping mall includes a flat fee of $3 plus $2 for every hour. Let C be the total cost after T hours. Write a function for C. So we know that we have a flat fee of $3, so it is a fixed fee, and then we have to pay $2 times t because we pay for every additional hour. So our equation C equals 3, so a constant fee plus 2t. B. Use your GDC to graph the function. So we have to type our function into our GDC to graph function and then redraw it on the paper. So this is our graph. You can do it also manually, just substituting the numbers, for example 1, 2, 3, 4, 5, how many you want, and then just plot these points and then draw a straight line. And in C, determine the cost after 5.5 hours. So basically we have to substitute 5.5 into our function. So C equals 3 plus 2 times 5.5. So this is 3 plus 11, so 14. D is the function proportional justify. So if you watched the previous video, we had the same problem to justify whether the function is proportional or not. And firstly, our function has a fixed fee, so this 3, so it means that it's not proportional. And secondly, our function doesn't go through the origin, so it doesn't pass through the point 0, 0. So it's not proportional. So your answer can look like this. Problem 2. A bacterial population doubles every 3 hours. Initially there are 100 bacteria. A. Write a function P representing the population after T hours. And in order to do that, firstly we can recall our general formula for exponential function. So P equals, and firstly we have P0, so the initial amount of something, in our case of bacteria. Then we have times B, and B is the growth factor. And then we have power, so in our case T. So we can rewrite our our function with substituted values. So we know that P0 is 100 because it's our initial amount of bacteria. And then we have times 2 because 2 is our growth factor because a bacterial population doubles. And then if we have every 3 hours, we have to write T over 3. If you are not sure how it works, this power, you can watch the previous videos because I explained it in more detailed way. Here you should remember that here we have our growth factor, and when we have every 3 hours, so we have our variable over 3. B. Use your GDC to plot the graph from T0 to T24. So we have to type our function into our GDC and then redraw the function. And this is our function. C After how many hours will the population exceed 5,000? So in other words, our P has to be greater than 5,000, and we can simply solve it on our GDC by choosing gsolve, then x calculate, and then y is 5,000, and we have t that is 16.9. So after 16.9 hours. And D, interpret the y-intercept and what it represents. So we can observe from our graph that our y-intercept is 100 because it's our initial population, and basically that's our answer. Problem 3. A small business sells items for $P each. The number of items sold per day is modeled by n equals 100 minus 5p. The revenue is R equals P times N, and in A, find the expression for R. So we know that R is P times N. From our command we know it. So R, and in brackets P, is P, because this is our $P each, and we can substitute our N, so 100 minus 5p, because this is our N, and now we can simplify it. So P times 100, so 100p minus 5p squared. And this is our expression for R. And in B, we have to use our GDC to graph R, so we have to type our function into our GDC and then draw it on the paper. So this is our graph, and C, what price maximizes the revenue. So maybe you already know it because when you were graphing this function, maybe you remember where is our vertex. So it's of course at P equals 10. And in D, we have to write down the maximum revenue, so basically revenue that is corresponding to our maximum maximum price, so it's 500. Problem 4. A car must travel a fixed distance of 180 kilometers. The time it takes in hours depends on the speed v in kilometers per hour, and is given by t equals 180 over v, where v is greater than 0. A. Graph this function on your GDC for v from 10 to 200. So we have to type our function into our GDC and then redraw it on the paper. So this is our graph, and you can observe that our function never touches y-axis nor x-axis. And in B, we have to explain the behavior of the graph as v goes to 0 and then as v goes to infinity. So we can observe that when v goes to 0, so here it goes to 0, our t goes to infinity. You can observe it here, that our t goes to infinity. So when v goes to 0, t goes to infinity. And on the other hand, when v goes to infinity, so in this way, our t goes to 0. So v goes to infinity, t goes to 0. See what speed gives a travel time of 2 hours. So we are given the time, so 2 equals 180 over v, because we have to look for v, what speed. So we can solve it manually or on our GDC. So maybe we can firstly times v, so 2v equals 180, and then divide both sides by 2, so v equals 90. So speed is 90 kilometers per hour. D. Interpret any asymptotes. So as you can observe, I mentioned it previously that our function doesn't touch any of the axes. So it means that we have two asymptotes. First is vertical, so at x equals 0, and the second one is horizontal at y equals 0. So this is our vertical asymptote, and this is our horizontal asymptote. And this is our final answer. And that was the last exercise from this topic, application of functions. It's basically how we use our functions in real life. And if you found this video helpful and useful, please leave thumbs up, subscribe to my channel, and in case of any questions or any doubts, feel free to reach me out in the comments down below or via my mail that is in the description of this video. See you!